Identification of homogeneous differential equations. Welcome, everyone. Before we dive into today's new topic, let's take a quick moment to reflect on our previous lesson, where we explored the properties of homogeneous functions. Now, we are going to take that foundational concept and apply it to a much more specific area of calculus. Specifically, we are going to learn how to identify a particular type of first-order, first-degree differential equation, which we call a homogeneous differential equation. By the end of this session, you'll be able to distinguish these equations from others using a few very reliable methods. Conceptual definition. First, let's look at the standard setup. We usually write a first-order, first-degree differential equation in the form di by dx equals f of x comma y. This simply means the rate of change of y with respect to x is equal to some function that depends on both x and y. So, when do we call this specific type of equation homogeneous? We use that term if the function on the right-hand side, which we called f of x comma y, is a homogeneous function of degree 0. Now, what does degree 0 actually mean in practice? It means that the expression on the right-hand side must remain completely unchanged even if we scale our variables. Specifically, if we replace every x with lambda x and every y with lambda y, the overall function should stay exactly as it was. To put this into a formal mathematical notation, we express this as f of lambda x comma lambda y equals lambda to the power of 0 times f of x comma y, which ultimately simplifies back to just f of x comma y. If you see that the lambda terms disappear and you're left with your original function, you've successfully identified a homogeneous equation. In the next slide, I'll show you two specific methods you can use to test for this. Now that we've recalled what a homogeneous function is from our previous lesson, let's look at how we actually define a homogeneous differential equation. 2 methods of identification. Now that we have established the conceptual definition of what makes a differential equation homogeneous, you might be wondering, how do I actually prove this in practice? Well, there are 2 distinct methods you can use to identify these equations. First, let's look at method A, which we call the lambda substitution test. This is the most formal and rigorous approach. To use this, you simply take your variables, replace every x with lambda x, and every y with lambda y. As we will see in the upcoming examples, the goal here is to simplify the expression. If all those lambda terms cancel out completely, leaving you with your original function, f of x and y, then you have successfully proven the equation is homogeneous. Alternatively, if you are looking for a quicker way, you can use method B, known as the ratio test. This method is a bit more intuitive. You check to see if the entire right-hand side of your equation, which we've called f of x and y, can be rewritten using only the ratio of y over x, or perhaps x over y essentially. If you can manipulate the equation so that the derivative di dx equals a new function, let's call it g, of the ratio y over x, then you can immediately conclude the equation is homogeneous. In the next few slides, I will walk you through some step-by-step examples so you can see both of these methods in action. Step-by-step examples. Now that we have covered the theoretical definitions and the 2 methods of identification, let's put that knowledge into practice with our first concrete example. Our goal here is to determine if the following differential equation is homogeneous. Di by dx equals the quantity x squared plus y squared, all over x times y. To solve this, we will follow a systematic approach. Step 1. We first identify our function, which we call f of x and y. In this specific case, f of x and y is equal to the quantity x squared plus y squared divided by x times y. Step 2. We will apply the lambda substitution test that we discussed in the previous slide. We are going to replace every x with lambda x and every y with lambda y. When we plug these into our function, we get f of lambda x and lambda y, which equals the quantity lambda x all squared plus lambda y all squared all over lambda x times lambda y. Step 3. Now we need to simplify this expression. When we expand those squares in the numerator, we get lambda squared x squared plus lambda squared y squared, all over lambda squared xy. Step 4, notice that we have a lambda squared term in both the top and the bottom. Let's factor out that lambda squared from the numerator and from the denominator. This gives us lambda squared multiplied by the quantity x squared plus y squared all over lambda squared multiplied by xy. Step 5, as you can see, the lambda squared terms in the numerator and denominator cancel each other out completely. This leaves us with the original expression, x squared plus y squared over x times y, which is exactly our original function, f of x and y. So, looking at our conclusion, because our substitution resulted in the exact same function we started with, meaning f of lambda x and lambda y equals f of x and y, we can confidently state that this differential equation is indeed homogeneous. In the next slide, we will look at a counterexample where this substitution fails to produce the same result. Step-by-step examples continued. Now, let's look at a contrasting case in our second example, where we'll identify a non-homogeneous equation. Our goal here is to determine if the differential equation, di by dx equals the quantity x plus y plus 1, all over the quantity x minus y, is homogeneous. Let's walk through the process step by step. First, just like we did in the previous example, we need to identify our function, f of x and y in this specific case. F of x and y is equal to the quantity x plus y plus 1 divided by the quantity x minus y. Next, we move to step 2, where we apply the lambda substitution test we discussed earlier. We will replace every x with lambda x, and every backslash lambda $y when we plug these into our function, we get f of lambda x and lambda y, which equals the quantity lambda x plus lambda y plus 1, all over the quantity lambda x minus lambda y. Now, in step 3, we attempt to factor out lambda to see if it cancels out. Looking at the numerator, we have lambda x plus lambda y plus 1. While we can factor lambda out of the first two terms, we run into a problem with that constant term, the plus 1. We cannot factor lambda out of the number 1. So, our expression becomes lambda times the quantity x plus y, plus 1, all over the quantity lambda times the quantity x minus y. Finally, in step 4, we compare this new expression back to our original function. Because of that lone constant term, the plus 1 in the numerator, the lambda in the denominator cannot be cancelled out. Therefore, f of lambda x and lambda y does not equal our original f of x and y. So, our conclusion is clear. This differential equation is not homogeneous. This perfectly illustrates the warning I'll mention later in the lesson regarding how standalone constants can break the homogeneity of an equation. Real-world context. Now, you might be wondering, why are we spending time learning how to identify these specific types of equations? They seem quite abstract and purely mathematical. Well, it is important to understand that these equations have real-world significance in fields like physics and engineering. They appear whenever the rate of change in a system doesn't depend on the absolute size of the variables, but rather on the proportion or the ratio between them. To give you a concrete example, let's look at chemical reaction models. Imagine you are tracking how the concentration of a substance changes over time. In certain scenarios, the rate at which this concentration changes might depend solely on the ratio of two different reactants. If we can express the rate of change, which we write as di dx, as a function that depends only on the ratio of y over x, then the system is governed by a homogeneous differential equation. This connection between the mathematical ratio and physical proportions is exactly what makes this concept so powerful. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. As we've seen in our previous examples, identifying these equations requires a very keen eye for detail, and it is easy to fall into a few specific traps. First, watch out for the mistake of ignoring constants. It is tempting to look at an equation where you see x and y in both the numerator and the denominator and immediately assume it is homogeneous. However, remember what we observed in example 2. That single, lonely constant, like +1 or -5, that isn't attached to a variable is a deal breaker. Because that constant doesn't scale with lambda, it breaks the homogeneity of the entire function. Second, be careful not to confuse your terminology. You might have heard the term homogeneous linear equation in other parts of your calculus studies, which refers to an equation that equals 0. Do not let that confuse you here. In our current topic, when we say homogeneous, we are specifically referring to the degree of the functions involved, specifically, that the function must be of degree 0. Finally, please pay close attention to your algebra during the substitution step. A very frequent error is incorrect power handling. When you are performing the lambda substitution, remember that the power applies to everything inside the parentheses. For instance, if you have x squared and you replace x with lambda x, you must write it as lambda squared times x squared. You cannot simply write lambda times x squared. If you forget to square the lambda, your entire test will be incorrect. Keep these points in mind, and you'll be well prepared for our final summary. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before you move on to your practice problems. First, remember the fundamental definition. A differential equation, where the derivative of y with respect to x equals a function of x and y, is considered homogeneous only if that function, f of x and y, is a homogeneous function of degree 0. This means the overall scale of the variables doesn't change the function's value. To identify these equations in your exams, you have two reliable tools. The first is the lambda substitution test. As we practiced in our first example, if you replace x with lambda x and y with lambda y, and the lambda terms cancel out completely, leaving you with the original function, f of x and y, then you have confirmed the equation is homogeneous. The second tool is the ratio test. This is often a much quicker way to check. If you can algebraically manipulate the right-hand side of your equation so that it is expressed entirely in terms of the ratio of y over x, or x over y, then you can immediately conclude the equation is homogeneous. Finally, I want to emphasize a crucial warning regarding the presence of constants. As we saw in our second example, be very careful with any standalone constant terms that are not multiplied by a variable. If you see a plus or minus a number, like a +1, that is just sitting there by itself, it will prevent the lambda terms from canceling out, which makes the equation non-homogeneous. Keep these points in mind, and you'll be able to identify these equations with confidence.